Hi there, everyone. We are going to talk today about sampling distributions for the difference in two means. And this is hopefully going to feel very similar to things that we've discussed before. But let's just start off with a quick example. So let's say that the heights of 10-year-old girls can be modeled by a normal distribution with mean mu sub g equals 56.4 inches, standard deviation sigma sub g equals 2.7 inches. So in other words, the individual heights of these 10-year-old girls look like this and have a mean of 56.4 inches. And if I were to draw and label this curve, I could add and subtract 2.7 inches to come up with the number of standard deviations. So that's the population of individuals. And then let's talk about 10-year-old boys. So their heights can also be modeled by a normal distribution with a slightly different mean and a slightly different standard deviation. And these, let's, discuss this. These are two independent populations, right? So two independent normal distributions. So suppose that we take two SRSs of 12 girls and 8 boys of this age and measure their heights. So we're going to have two independent SRSs. And from those two independent SRSs, we're going to have two independent X bars, an X bar sub G for the girls and an X bar sub B for the boys. And just as a quick reminder, the population of girls' heights had a mean of 56.4 inches and a standard deviation of 2.7 inches. That's for the girls. And then the population of the boys had a mean of 55.7 inches and a standard deviation of 3.8 inches, right? And we took two separate independent simple random samples. So what do we know about these two independent sampling distributions? So the sampling distributions for the girls are on the left-hand side. Because of the central limit theorem and because the population distribution is normal, we can say that the sampling distribution is also approximately normal. So the sampling distribution for X bar is approximately normal. We know that the center of the sampling distribution is equal to the population mean, right? And we know, what do we know about variability? We know that the standard deviation of the sampling distribution is that formula right there, sigma over root n, right? And we have to check the condition, the 10% condition, to be able to use that formula for variability. So we can definitely say that 12 is probably 10% of all 10-year-old girls, less than 10%, sorry, of all 10-year-old girls in the United States, right? So this is what we know about the sampling distribution of X bar. Now, for the boys over on the right-hand side here. So again, we said that the population distribution was approximately normal. So because of that, the sampling distribution is also going to be normal. Think central limit theorem, right? We can say that the center is equal to the population mean. And we can say then that the standard deviation of the sampling distribution, use that formula. And again, we have to check the 10% condition right down here. Okay, so now what if I calculate the difference between those two sample means that I came up with? So remember our rules for linear combinations. If I combine two distributions, in this case, combine two sampling distributions, we know that if the original shapes were both normal, the sum or the difference is also going to be normal, right? So here's a simulated sampling distribution of the difference in the two sample means. notice the shape. It looks approximately normal. If I were to take, for example, one set of samples, maybe one mean for the girls was 56.09 inches and one mean for the boys was 54.68 inches. And if I were to calculate that difference, and just one thing also I want to point out is that we're specifying that we're calculating the difference, like the difference in the mean for the girls minus the mean for the boys. So if I had switched that, if I did mean for the boys minus the mean for the girls, all these values, it would be like basically like a mirror image, flip-flop. So all the negatives become positives, positives become negatives. So anyway, in this case, this one set of samples down here gives us a difference of 1.41 inches. So 1.41 inches is that red dot. So again, if I were to sample a second time, a second different sample of girls and different sample of boys, calculate their average heights, maybe it would represent, maybe the difference was 2. So it would represent like one of those dots right there, right? So this is a whole bunch of simulations. And we just talked about the fact that this difference, the shape would be normal because both of the original sampling distributions were normal. And if we take two distributions and subtract them to find the mean of this new distribution, we subtract the means of the two sampling distributions, right? And the standard deviations, remember, whether we add or subtract the two distributions, standard deviations, we always have to add the variances. So my formula for standard deviation, standard deviation of a sampling distribution for the girls is going to be sigma over root n, right? And then the standard deviation for the sampling distribution of the boys is sigma over root n, right? And let me specify girls and boys. So I can't add them, I can't subtract them. What I have to do is square each of them, right? So if I square each of them, I get sigma squared girl over n, right? And then I take sigma squared boy over n. So those are the variances, and then I can add the two variances, take the square root. So that's where this formula right here comes from, right? It's not magic. It comes from the original formula for standard deviation of a sampling distribution for means, and then I take each of those values, square them, add them together, take the square root. So the standard deviation of this new sampling distribution for the difference in the two means is this value here, this 1.55 inches. And again, in this green box, it just is a reminder that these formulas aren't magic. They all come from what we know about combining random variables. All right, let's kind of summarize here. So if we choose an SRS from one population and an SRS from a second population, and one of the key words here is that they have to be independent SRSs. The sampling distribution of the difference between the two means is going to be normal if our central limit theorem condition is met for both populations, right? So we could either say, all right, if both population distributions were normal, just like the example we just saw, then the difference in the new population is also going to be normal. Or if both sample sizes are large, both bigger than 30, then the difference is going to be approximately normal. Or we could say if one population is normally distributed and the other sample size is large, the difference is still going to be normal. So as long as both populations or both sampling distributions meet the central limit theorem, then the difference is also going to be normal. Okay, so the mean of the sampling distribution of x bar 1 minus x bar 2 is that. And then the standard deviation, we just talked about that formula. But again, keep in mind, we have to check the 10% condition for both samples, right? Okay. So just a couple quick notes on conditions. Remember, we talked about conditions are like really one of the most important parts. We need independent samples. So we need an independent sample from independent populations, and we need independent observations within each sample. So in other words, the 10% condition needs to be met. And then this is just quickly our interpretation of standard deviation. And the standard deviation interpretation for the difference between two means is the same exact as it was for the difference between two proportions. So read this, make sure you understand what it's saying. And remember, standard deviation is basically how far on average does each individual value differ from the mean? Well, remember, the mean in this case is actually the difference in the population means, right? And then the individual observations are the difference in the sample means. So it's how far is the difference in the sample means going to vary from the difference in the population means on average. Okay, let's look at an example. A fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large drink cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid dispensed by the machine follows a normal distribution. So they're telling me with mean 27 and standard deviation 0.8, right? When the medium setting is chosen, the amount of liquid dispensed follows a normal distribution as well, but the mean is 17 and the standard deviation is 0.5, right? So I a lot of times like to write this information down. There's a lot of stuff to keep track of, right? All right, so to test the manufacturer's claim, the restaurant manager measures the amount of liquid in each of 20 cups filled with the large setting and 25 cups with the medium setting. Okay, so there's all the information I need. Let X bar sub L minus X bar sub M be the difference in the sample mean amount of liquid under the two settings. What's the shape of the sampling distribution of the difference and why? Well, remember, they told us, I underlined here in red and here in red, that both of the population distributions are approximately normal, and therefore the shape of the sampling distribution of the difference between these two are also going to be normal, right? And that's part of the central limit theorem. Let's find the mean. Well, my formula for mean, and look at that notation, the mu of X bar L minus X bar M is going to be equal to the difference between, really, this is the mean of X bar L minus the mean of X bar M. And the mean of X bar L is equal to mu of L minus mu of M, right? Standard deviation, let's calculate it and interpret it. Okay, so this is our new crazy formula. And keep in mind, this is on the formula sheet. You should locate this on the formula sheet. So we can only use this formula, though, if we either check for the 10% condition or really if I have independence. But in this case, because I'm not sampling without replacement, so I have like an infinite population. If my in this case, my population is all the cups that are being dispensed from this machine or whatever, right? And so because I have an infinite population, I didn't sample without replacement. Remember, our 10% condition is when I sample without replacement. And because I'm not sampling without replacement, I don't need the 10% condition. But I still need to indicate that the amount of liquid in each cup is going to be independent from one another. And then my interpretation is that the difference in the sample mean amounts of liquid typically varies by about 0.2 ounces from the true population difference in the means, which we calculated a second ago was 10 ounces. All right, so why do we do all this stuff? We do all that setup so that we can answer question D. Let's estimate the probability that the difference in sample means is within 0.25 ounces of the true difference in means. So in other words, look at this picture here. I want the probability that the difference in the sample means. So the difference in the sample means is X bar L minus X bar M. And notice my sampling distribution, my normal distribution that I draw here in that picture, I'm not talking about individual, amounts of liquid in individual cups. I'm not talking about the averages in just large cups. I'm talking about taking two samples, one from the large, one from the medium, and calculating the difference over and over and over and over. So X bar L minus X bar M. And we want the probability that the difference in sample means is within 0.25 ounce of the true difference in means. Well, we said that the true difference in means, right? So should have been, this value here should have been 10 ounces, right? So within 0.25 ounces of that means we want the difference to be between 9.75 and 10.25. And you can see that I have that marked off on my picture here and here. So I want the area within the curve there. So I can use a z-score, I can use normal CDF, whichever one I choose. But if I use normal CDF, I should have something like this written down, labeled, and my answer is 77.74%. That's it for section 7.3 and talking about sampling distributions for the difference in two means. Thanks so much for watching.